Hello, welcome to the Extraordinary, where we are committed to the relentless pursuit of excellence. If you love tech, you want to skill up, or you just like learning new things, subscribe to the channel so that you don't miss any of our content. We're going to be continuing with classes, and in today's episode, we'll look at inheritance and some other concepts. Inheritance is a way for you to derive a class from the definition of another class. For example, let's say we have a class called shape. Let me create a new class here. So create a new class, shape.py, and in here I'm going to define class of shape, and then I'm going to define the init. Here we have self and sides. The sides will be equal to 3 by default. So self.sides is equal to sides. Then I'm going to define another function here. Let's say display define, let's say override display. So self, and here I'm going to print this is a triangle. Then I'm going to create another class. Let's call this quad.py. Say, let me just take everything in shape, copy, paste. We're going to make some adjustments. The sides here is going to be 4 by default. Then override display, this is a quadrilateral. Save that. Then I'll create an example file, example9.py. Before I do this, I have to come back in here and change this to quad and shape. Now this is how we inherit from the shape class. Here we're saying the quad is a subclass of the shape class. We have to import, let's say, from shape, import shape, so that we have access to this shape class here that we are inheriting from. Now let's proceed. In here we're going to say from shape import shape, and from quad import quad. Now we can define try as a shape, and we can define quad as a quad. And if I come in here and say try dot override display and quad dot override display, when we run this or when we execute it, we say Python example 9, we get this is a triangle and this is a quadrilateral. So this quad is inheriting from the shape class, right? Now we do not need to overwrite the definition, because what we're doing here is we're overwriting the definition of the override display. We can extend this method instead, and how we do that is, let's create another example here, another method here. Let's say extend extend display. And here what we're going to say is if sides self.sides is equal to 3, then we print this is a triangle and return. Otherwise, here in the quad class, copy this now, paste. Now instead of us overwriting, we are going to extend display in the shape class. Since we're inheriting from it, we have access to this method. So how do we do this? Save. Here we're going to call and say shape dot extend class, and we'll pass in the self argument, pass that into the extend method of the shape class. Now what is basically going to happen is if the size is 3, which means that it's an instance of shape, then it's going to call this shape and it will just return after it has called it. But if that is not the case, which means it's an instance of quad, it's going to continue and say self.sides equal to 4, then it will print this is a quadrilateral. So let's see that example. Comment this out, get it. Let's highlight this too and change it to extend display and save. Now if I run this, I get this is a triangle. What about for quad? I did not get anything. Why? Self.sides. Oh, sorry. Extend display. Now if I run this, this is a quadrilateral, this is a triangle, this is a quadrilateral, and we understand what's going on. It's because I am extending the extend display of the inherited class or of the parent class, which is shape, and I'm adding extra functionality to it. We can determine which object is an instance of a class and which class is a subclass of another class using the is instance and its subclass function respectively. Let's see an example of that. So we could ask, let's print is try an instance of shape. This is going to be true because try is actually an instance of shape. So we say is instance, I'll pass in the object try, I'll pass in the class shape. Run this. Is try an instance of shape. That's true. Now what about is try an instance of quad? That will be false because it is not an instance of quad. Let's see. Print false. Now the next one is try an instance of, not try now, sorry, is quad an instance of shape. Quad is it an instance of shape? Let's see what we get. What do you think it will be? Drop your answer in the comment before we check it. Now let's run it. Is quad an instance of shape? Is true. Why? Because shape is a super class or a parent class of quad and of quad, the quad class now, and this quad object is an instance of quad, so it is also an instance of shape because quad inherits from shape. Now next, what do we have? Let's ask if quad is an instance of quad. Of course that will be true. Let's just check it. Quad is an instance of quad. And what do we get? Yes, it's true. Now let's check for subclass. So we check print is quad a subclass of shape. And what do we get? Is subclass is quad a subclass of shape. And we get true. Why? Because yes, it's actually a subclass of shape. Now what if we switch it? Is shape a subclass of quad? That will be false because shape is not a subclass of quad. So let's check. Is shape a subclass of quad? What do we get? That's false, right? Which is what we expect. Now we are not limited to inheriting from just a single class like we did here, where we just inherit from shape. We can inherit from as many classes as possible, so it follows a depth first, left to right pattern. So it first check for attributes in the left base class, so recursively checking all the base classes of that class, and then move to the next one and the next, all the way until it finishes it. Personally, I am not a fan of this level of inheritance, but Python allows you to do that, which is fine, I guess. Also, you could have private variables. Now, private instance variables that cannot be accessed except from inside an object don't exist in Python. However, there is a convention that is followed by most Python code. So a name prefix with an underscore, for example, something like this, should be treated as a non-public part of the API, whether it is a function, a method, or a data member. It should be considered an implementation detail and subject to change without notice. So by convention, any member or any name of a class that has underscore in front of it is treated as a private member of that class. Since there is a valid use case for class private members, namely to avoid name clashes of names with names defined in subclasses, there is a limited support for such a mechanism called name mangling. Any identifier of the form underscore spam, as like this, that is with at least 2 leading underscores and at most 1 trailing underscore, is textually replaced with underscore class name underscore spam, where class name is the current class name with leading underscores stripped. This mangling is done without regard to the syntactic position of the identifier, as long as it occurs within the definition of a class. So let's see an example of name mangling. I'm going to create a new file here, say example 10. Inside our classes directory, say example 10.py, and inside this we're going to create two classes where we say class mapping def init underscore self iterable self dot items list equal to empty list, and then self dot underscore update iterable. Then we have def update self iterable for item in iterable self dot items list dot append item. Now we'll say underscore update is equal to update. So this is a private copy of the original update method. Now we can define a subclass here, mapping subclass, which inherits from mapping class, and then in here we're going to say def update self keys values, and here this provides new signature for update, but does not break init. Now let's write, say for items in zip keys values self dot items list dot append item. So this is item in this, right? So basically what's happening here is we have our update method defined in the parent class mapping, and we are using this update method to perform some operation in the init, that's like the constructor, right? But we want to modify or override this update function in our subclass. Now modifying this update function directly in our subclass is going to lead to breaking code in the init function. And remember, this init function is also being called by the subclass. So by using this underscore update and assigning this update method to it before calling it on in the init, we are essentially preserving this update as a private method. So that way we can now redefine update in the subclass without breaking the init method. The above example would work even if mapping subclass were to introduce an underscore update identifier, since it is replaced with underscore mapping underscore update in the mapping class, and underscore mapping subclass underscore update in the mapping subclass class respectively. Note that mangling rules are designed mostly to avoid accidents. It is still possible to access or modify a variable that is considered private. This can even be useful in special circumstances, such as in the debugger. Notice that the code passed to exec or eval does not consider the class name of the invoking class to be the current class. This is similar to the effect of the global statement, the effect of which is likewise restricted to code that is byte compiled together. The same restriction applies to get attribute, set attributes, and delete attributes, as well as when referencing __dict __ directly. If you do not get any of that, don't worry about it. Let's just proceed with what we are doing. The long and short of the whole story is that we can use this syntax to essentially create private variables or private names or private methods. Sometimes it is useful to have a data type similar to the Pascal record or C-struct, bundling together a few named items. The idiomatic approach is to use data classes for this purpose. So we can define a class, which is a data class, and then we can now define an object of that class or an instance of that class and use it as though it were a normal class. A piece of Python code that expects a particular abstract data type can often be passed as a class that emulates the methods of that data type instead. For instance, if you have a function that formats some data from a file object, you can define a class with methods read and readLine that get the data from a string buffer instead and pass it as an argument. Instance method objects have attributes too. m__self__ is the instance object with the method m, and m.__funct__ is the function object corresponding to that method. So this is where we are going to stop for classes today. In our next episode, we are going to continue with iterators. If you enjoyed the content, remember to like and subscribe and share with your friends, and I'll see you in the next one. Bye.